Hello and good morning. Welcome to webinar number 3. This is EBIO's third webinar in a series of webinars showing the results of this amazing research project. This morning, we're going to hear about the upgrading of pyrolysis liquid into biofuel, opportunities and the challenges. We have speakers from Tüpras, Seda and Jan, and we also have Yannick from ITQ. So just a couple of housekeeping rules before we start. If you have any questions, please use the question and answers box at the bottom of the screen. You'll see it, or wherever your bar is, there's a Q&A box. So write your question in there and it will either be responded to in written form during the webinar, or at the end, we will have questions and answers after the two presentations. If you'd like to say hello to your fellow colleagues or you have any technical issues, you can use the chat box and we'll be monitoring that. Okay, so without further ado, I'll hand over to Roman and he will be giving you a quick overview of the EBIO project before our speakers start today. So please, Roman, the floor is yours.
Thank you, Emma.
Great.
Welcome everyone also from my side. In this webinar, we will talk about the last part of the value chain of EBIO. As most of you already know, in this project, we use electrochemical methods to turn bioliquids into fuel precursors, and then we co-process them using refinery technologies into fuels. And we have had 2 webinars in April and May, which were dealing with the bioliquids themselves and with the electrochemical conversion. And today we have the final webinar of this series dealing with the refinery operations and co-processing of those upgraded bioliquids. As Emma already said, we have 2 presentations and 3 speakers. The first presentation will be given by Seda and Can from Tüpras, and then the second one by Yannick from ITQ. And we start with Seda. Please, Seda, the floor is yours.
Thank you, Roman and Emma, for the introduction. Welcome you all to the third webinar of the EBIO project. I am Seda Karan from Turkish Petroleum Refineries. I am the product owner of the renewable fuels at R&D department. Today, together with my colleague Can Güvenç and our project partner from CSIC-ITQ, Yannick Mathieu, today we will have a look at pyrolysis liquids from a biofuel point of view. Let me give you a brief introduction about Tüpras, which is a refining company producing the energy of Turkey for almost 70 years. Together with over 6,000 employees in 4 different refineries and headquarters in Istanbul and trading office in London, it is the largest enterprise of our country. After its first establishment in 1955 as a public company, its privatization to Koç Group has occurred in 2005. By the investments after that point for both modernization and the residue upgrading, which is completed in 2014 in Izmit refinery. Today, Tüpras has 30 million tons of crude oil processing capacity. For the transportation of crude oil to 4 refineries which are located in Izmit, Izmir, Batman and Kırıkkale. In addition to the pipelines from Iraq and Bakü-Ceyhan, Tüpras has some subsidiaries, Körfez Ulaştırma and Ditaş for railway and maritime logistics. OPET is our associate for the distribution of value-added products through 5 different terminals and many stations all over the country. By trading office established in 2018, our sales limit expanded and we ensured that our products reach 15 countries. And 2 years ago, by holding the shares of ENTEC, which is a zero carbon electricity company, Tüpras took a pioneering step through strategic transformation. In 2021, with the Paris Agreement signed by Turkey and the announced 2053 net zero target, Tüpras initiated its transformation plan by taking steps regarding changing demands and environmental concerns, focusing on 4 main areas, which are biofuels, zero carbon electricity, clean hydrogen, and sustainable refining. Tüpras declared its transformation plan 2 years ago. As the first phase of its investments for biofuels, especially sustainable aviation fuel, Tüpras signed a licensing agreement with UOP Ecofining HEFA technology, which relies on the waste vegetable oil and fats. The estimated capacity will be 4,000 tons of feedstock annually. We are also looking for some other alternative technologies to triple this SAF capacity production after 2035 and taking a role as R&D department for the exploitation of these new routes for the development of new methodologies. At R&D Center, which is located in Izmit Refinery, there are 68 employees with the majority of human researchers. In addition to biofuels, we have many completed and continuing Horizon-funded projects in the frame of research focuses such as CCUS, circular economy, commercial and digital solutions. Besides EBIO, we have initiated another demo scale project, which is Fuel Up at the beginning of this year, which also aiming the conversion of woody-based pyrolysis liquids into both aviation and marine fuels. And we have 2 newly funded renewable fuel projects relying on microalgae and microbial oil generated from CO2, which are Sunfusion and Econic. Here I would like to continue with describing the share of transportation sector in global GHG emissions. Industrial sectors, including production, energy, and transport, account for over 40% of global GHG emissions. And total global emissions are unfortunately reached to 50 billion tons of CO2 equivalent. Transport sector is responsible for the 16% of all emissions. Aviation is one of the 6 hard to abate sectors like cement, steel, plastics, and shipping. Aviation takes part by 2 to 3% for now, and according to the European Commission, by the middle of this century, the demand for flying could increase and the GHG emissions will reach to more than 3 times compared to 2005 levels. Although this increase has been temporarily slowed down by the effect of the COVID-19 pandemic, it is recovering very fast. And in the last years, aviation emissions has already reached 80% of 2019 pre-pandemic peak. According to CORSIA, which is a carbon offsetting and reduction scheme, and it takes as the baseline reference the emissions of 85% of the emissions of 2019. Precautions for aviation can be collected in 3 fields to stabilize the emissions at that level. These are operational improvements, aircraft technologies, and clean fuel technologies. To draw back the emissions to baseline, estimated contribution of these technological advancements and operational improvements are very limited without sustainable aviation fuels. In addition to sustainable aviation fuel, there are other alternatives like hybrid electric and hydrogen that can pave the way for decarbonization of aviation, but especially for the commuter and regional jets. The reason behind why batteries are limited to shorter distances is their volumetric energy densities. That's to say, a plane would need more than 50 kilograms of batteries to replace just 1 kilogram of kerosene, which is jet fuel. And they can be used for a maximum range of 500 kilometers to 1,000 kilometers. While the mass energy density of hydrogen is higher than the kerosene, liquefaction is required for both safe distribution and storage purposes. On the other hand, SAF, which is a kind of liquid fuel already, and it is both chemically and physically compatible with fossil jet counterparts, and therefore it is the most promising way of decarbonization. Also, considering that the 70% of jet fuel consumption already comes from the medium and long range flights, SAF is the major solution for the aviation. In Europe, pursuing the ambition of being a global leader to accelerate independence to fossil fuels, European Commission completed the adoption of Renewable Energy Directive, and the third version entered into force in the last November. By the new directive setting the targets and obligations in many sectors, the renewable energy use target in transport sector by 2030 was increased to 29%, and an alternatively 14.5% GHG reduction must be ensured. Although the previous versions covered the road and rail transport, now it is extended to all transportation sectors, including aviation and maritime. Together with a mandate encouraging the use of advanced biofuels from Part A feedstocks, which are mainly non-food biogenic feedstocks. Also, the cap for the use of Part B feedstocks, which are used cooking oil and animal fat, and the sources which HEFA relies on. This cap, 1.7%, is retained in this version also. Aviation Specific Refuel EU initiative aims SAF blends starting with 2% in the next year and gradual increase to achieve 70% year by year to reach 70% in 2050. While the target sounds very ambitious, current SAF capacity of EU and UK is now less than 1% of total aviation fuel. And also the majority of SAF plants coming online over next 5 years rely on HEPA technology. When we look at the major renewable fuel technologies, to sketch them all in one is very difficult and complicated. To simplify it, we can group with respect to the feedstocks. Oils and fats group of feedstocks undergo initially a pretreatment for reducing the gum content, phosphorus, and chloride content. And they can later undergo either transesterification for biodiesel formation or hydroprocessing for biokerosene, renewable diesel, or bionaphtha formation. The lipids from algae should be extracted, again may undergo in the same route. From sugar or starch-based feedstocks, you can either use hydrolysis or fermentation technologies. In fermentation, you can convert them into alcohols, mainly ethanol and isobutanol, which may later undergo a series of catalytic reactions like dehydration, oligomerization, and hydroprocessing. Lignocellulosic biomass and waste may again go through this alcohol route, or there are two more options for them. They can be either gasified to generate a biosyn gas, then undergo polymerization through Fischer-Tropsch reaction to obtain different length of carbon chains, or they can be pyrolyzed and treated by hydrodeoxygenation and hydrotreatment. According to the Global Renewable Fuel Project Tracker of Bloomberg, the hydroprocessing through HEFA technology will reach a saturation starting from 2027. By 2030, alcohol-to-jet and e-fuel technologies will have some small proportion to fill the gap. However, through this feedstock limitation, HEFA can only satisfy about only 4% of total global jet fuel demand. With the additional capacities of alcohol-to-jet and e-fuel technologies, this capacity will reach 21 million tons in the world. By so far announced projects, this will only represent 5.4% of global jet fuel consumption. Obviously, from that year forward to achieving the goals of subsequent years, the capacities should be raised and alternative routes must be added. When we look at the ASTM approval status of this pathway, so far 8 standalone and 2 co-processing pathways for SAF production have been certified by ASTM. Although the availability of biomass and municipal solid waste is high, however, the maturity level of these technologies are not ready to be commercial. Pyrolysis is a promising technology that has to receive ASTM approval. It could become a comparatively cheap alternative with feedstocks, including abundant and relatively inexpensive agricultural and forestry residues. PTL is one of the most advantageous pathways for emission saving with unlimited carbon source that can be directly captured from the air or point sources. However, technologies are required for this direct air capture and to reduce the green hydrogen prices and electricity prices, actually. Therefore, the potential of PTL will occur mainly after the 2030s, maybe 35. To just remember the pyrolysis process, pyrolysis is the thermochemical conversion of biomass into bio-oil, gases, and some solid products, which are called as biochar. This biochar can be used either as fertilizer or for some water purification applications, or you can directly use it for the process heat. In pyrolysis, the biomass is initially pre-dried and converted into chip form before being treated in the reactor at around 500 Celsius degree and in the absence of oxygen. The residence time of material is very short, just a few seconds. After the removal of biochar through cyclones, the bio-oil and gas fractions are obtained and separated. When we look at the distribution of the products in the fast pyrolysis liquid, bio-oil proportion is around 40 to 60%. Along with biochar, it is around 10 to 15%. And the remaining part is the gases, which are composed of hydrogen, methane, carbon monoxide, and carbon dioxide. Wide range of biomass feedstocks, as I said before, provides a flexibility for the pyrolysis. And you can also contribute to waste reduction in this way. Pyrolysis represents a promising pathway, but some further challenges are remaining, and some development activities are required to make these bioliquids more refinery friendly. We should decrease its acidity and oxygen content. Also, due to the high moisture content, it is highly affected from the transportation costs. Therefore, construction of pyrolysis plants near or close distances to the source becomes economically much more viable pathway. In 2022, the pyrolysis oil share of EU was just 3.6% with around 200K ton per year. The reason for low capacity is the limited number of pyrolysis plants, and some of them are already used for the plastic and the used tire pyrolysis. On the other hand, for Europe, 125 million tons of dry woody biomass and agricultural residues is estimated per year, and only less than actually 1% is used for pyrolysis for renewable fuels. For Turkey, this capacity is around 40 million tons. If all these additional capacity were used for pyrolysis, it may bring about almost 20 million tons of SAF for Europe and around 5, 6, 7 million tons for Turkey. Therefore, it is really worth to discover and reveal this untouched potential to achieve 2050 goals. It is all from me for now, and now my colleague Can Güvenç will tell us about the state-of-art on hydroprocessing of pyrolysis liquids and our studies in EBIO project.
No, thank you, Seda. Yes, okay. Also, due to the high all right. Okay. Hello, I'm Can Güvenç. I have been working as a researcher at Tüpras for about 1 year, focusing on renewable fuels and pilot plants. Today, we will discuss some of our work on pyrolysis oil, hydroprocessing units, hydrodeoxygenation reaction, and the EBIO project. As Seda mentioned, pyrolysis oils have several advantages and challenges, significant developments in pyrolysis oil technology. For bio-oil production that back to 1980s, these studies have increased significantly in the last decade, and it has become commercial. I will talk about some companies in the field of biomass-based renewable fuel production. First, let's start with Preem Refinery. Preem is in Sweden, and it's reduced biofuel from materials such as wood chips. It turns them into gasoline and diesel fuel. Preem aims to increase its biofuel production capacity to approximately 5 million cubic meters by 2030. Another important company is Green Fuel Nordic. Green Fuel Nordic, based in Finland, operates a bio-oil refinery in Lieksa using BTG bioliquids technology. This facility producing 24,000 tons of bio-oil. Envision Technology is a joint venture between Honeywell UOP and Ensign. Biomass heated to 500 degrees bio-oil can be used for heat and energy production or convert into transportation fuel. Finally, let's talk about Ensign. Ensign uses RTP technology to convert biomass into high-yield bio-oil. This technology is used in 15 commercial scale facilities worldwide. After discussing these works, I would like to explain the process of producing sustainable aviation fuel, SAF, from various feedstocks. Our journey begins with the collection and preparation of various feedstocks such as oils, fats, solid waste, carbon dioxide, renewable energy, wood, and agricultural residues. These feedstocks gathered and processed to make them suitable for the next stage. The first major processing step involves the gasification unit. In this unit, solid carbon-based materials like wood and agricultural residues are converted into syngas, a mixture of hydrogen and carbon monoxide. Through partial partial oxidation at high temperatures, this syngas essential for subsequent chemical process. Next, we move the pyrolysis oil, where organic materials such as solid waste thermally decompose in the absence of oxygen. This process helps convert various waste materials into useful intermediate products. In parallel, there is an electrolysis unit. Here, water is separated into hydrogen and oxygen by electrolysis. The hydrogen produced here is critical for hydrogenation process in the reverse water gas shift reaction. We convert carbon dioxide and oxygen into carbon monoxide and water. This step increases the carbon monoxide content of the syngas. The syngas then enter the Fischer-Tropsch synthesis, where it's catalytically converts in the long chain hydrocarbons. These units produce synthetic crude oil by converting syngas into mixture liquid hydrocarbon. We use FCC unit to process heavy hydrocarbons. Here, the heavy fractions are broken down into lighter. More valuable products like gasoline and diesel used in catalyst and high temperatures. The final refining step takes place in hydroprocessing unit. In this unit, the synthetic crude oil produced by the Fischer-Tropsch process is upgraded to SAF. This involves hydrocracking and hydroisomerization process, removing impurities and converting hydrocarbons into high-quality jet fuel using hydrogenation. Speaking of SAF, let's take a look at the characteristic of SAF fuel. Shall we? When we look at the specifications for SAF, we see that co-processing must be done for ASTM D1655. If we want to use this product as jet fuel, we need to reduce total acidity. The final boiling point should also be a maximum of 300 degrees Celsius. The density should be between 775 and 840 kilograms per cubic meter. And the freezing point, this is another important value. We need to achieve, we must meet the maximum freezing point of minus 47 degrees. To meet these properties in pyrolysis oil, we first need to reduce the high oxygen and water content. For this, we can use hydrodeoxygenation reactions. Now, let's explore these reactions. These reactions are crucial for converting bio-oil and other renewable feedstock into valuables and chemicals. In the fuel production, they are effective in converting olefins and paraffins and isoparaffins. This plays a critical role in determining quality and performance of the fuel. Why are these molecules important and what do they do? When we talk about olefins, we are talking about more reactive molecules. They are prone to oxidation and polymerization reactions, which can negatively impact the fuel stability during storage. I will give an example of this later. Also, olefin can have higher combustion temperatures, which can increase combustion efficiency, but may also cause more deposit formation at high temperatures. Looking at M-paraffins, M-paraffins generally have low freezing points, which is necessary for jet fuel to be used at high altitudes and low temperatures. Additionally, M-paraffins have high energy density, which increase fuel's energy efficiency. Isoparaffins, on the other hand, have branch structure. Therefore, isoparaffin have low freezing points, which improve cold weather performance. Isoparaffins are more stable and more resistant to oxidation reactions, which increase the long-term storage stability of the fuel. Carefully managing this conversion is critical to optimizing jet fuel performance. It is important to minimize the unwanted effect of olefins while benefiting from the useful properties of M-paraffins and isoparaffins. For these reasons, catalysts containing NEMO and COMO, which are effective in converting olefin, M-paraffin, and isoparaffin groups, are usually used as seen in the table. All right, but how do these reactions happen? Let's take a look. An aldehyde undergoes decarbonylation to form hydrocarbon and carbon monoxide. With the removal of the carbonyl group, a simpler hydrocarbon and carbon monoxide are formed. This reaction helps reduce the oxygen content of the feedstock. A similar logic applies to the carboxylation. A carboxylation group is removed from an organic molecule, resulting in the formation of carbon dioxide and hydrocarbon. Shall we look at the hydrogenation? It sounds a bit cool. This is the process of the adding hydrogen of the organic compounds with double or triple bonds. It sounds cool, and this reaction is very important in the H2O process because it helps saturate the feedstock, making it more stable and less reactive. The oxygenation is looking at us from over there, like a combination of other reaction. It is in fact, the oxygenation occurs through several mechanisms such as decarbonylation, decarboxylation, and direct removal of oxygen atoms as water. The oxygenation removes oxygen atoms from organic molecules. There is a Turkish saying that means the most famous solist comes on stage last. Here, our most famous solist is hydrocracking. It is the process of converting large hydrocarbon molecules into smaller, more valuable products like gasoline, diesel, and jet fuel. Just as a famous solist does not go on stage without guitarist, drummer, and vocal team, this reaction does not go on stage without high pressure, high temperature, hydrogen, and a catalyst. In the end, hydrocracking helps produce lighter and more valuable fuel products. All good, but in which system can we implement these reactions? Come closer, let me tell you about plants have at Tüpras. Do you get closer? Don't get too close. If I show too much of the facility, I might lose my job. The reaction I mentioned can be carried out our Tüpras R&D Center, where have our pilot plants or facilities include both pilot scale and lab scale system. I will go through this quickly. Everything is almost ready to perform the reaction, but we should also take a look at the status or potential feedstock. Yes, I have prepared a reader complicated page here to make. You forgot the previously image. Let's take a little journey. This journey will be about converting biomass and biologically drawing stocks in to valuable chemicals and fuels. First, let's design a journey starting from fatty acids. This abundant in vegetable oils, use cooking oils and animal fats. These fatty acids can be converted into free fatty acids various process. From the free fatty acids, we can derive resin acids and neutral substances. Things get a bit more complicated after this. I think we are Now, under the Fischer-Tropsch synthesis products on the graph, resin acids and neutral substances can be converted in various important chemical compounds. For example, alkanes, these can be produced by hydrogenation, fatty acids. Alkanes are very important as energy source and fuels. Aromatic compounds, these are usually obtained process like pyrolysis or hydrogenation. Ketones, these derived from the oxygenation of fatty acids. Alcohols can be produced by hydrogenation fatty acids. When I look at the molecules under pyrolysis and HDL oils, it reminds me of Real Madrid's Los Galacticos team. It is fantastic to get here from fatty acids. The team includes many players, and you can see distributions of these contents in the graph next to it. Carboxylic acids, ethers, furans, etc. Speaking of pyrolysis, let's also look at the properties of pyrolysis oils. Pyrolysis oils have a high content, which is the most disappointing part. They have between 45 to 50% oxygen, but don't be sad. There are stabilized pyrolysis oils, SPO. However, their content is still 35 to 40%. If you ask what else we can do, let me introduce you to stabilized deoxygenated pyrolysis oil, STPO. Their oxygen content is between 7 to 10%. High water content is also an important parameter. Likely, this below 1% for STPO. Remember the airplane presentation, where ASTM standards, one of the important parameters is the acid number, which needs to be 0.1 according to standards, but even our best candidate STPO has a value around 7. We are still far from obtaining jet fuel, but let's not lose motivation. Let me tell you about a project. It's called EBIO. In this project, we did some work to solve these problems. We think that if we could mix SPO with fossil feedstocks and feed them into the reactor, we could process them. And here we are looking at the photo at the top. Yes, SPO and STPO did not dissolve in diesel. Due to different densities and the presence of polar groups, complete dissolution did not occur. What can be done here? We decided to perform a SIMDIS analysis. You can see the graph on the right. If we fractionate SPO and STPO and remove the heavy fraction, we can adjust their properties to be closer to diesel oil or kerosene from the desired fossil feeds. Therefore, we did fractionation work. You can also see the heavy and light fraction of SPO and STPO in the graph. It seems like light fraction of SPO falls more within the desired range, but STPO is a bit further from the range. But I priced STPO to you earlier. Its acid number and oxygen content were more in line with what we want. So let's not lose motivation again. Let me tell you about some work we did with STPO. I priced NEMO containing catalyst a lot to you. We agreed to use this catalyst. We set our reaction temperature to 360 degrees Celsius and pressure to 19 bar. We feed STPO with hydrogen. By doing this, the reaction becomes a hydroprocessing reaction. This condition will be the same for all the work I will talk about from now. We took simplest every hour. You can see the colors of the products. They send a bit dark, don't they? In fact, after waiting a few days, they almost turn black. Earlier, I mentioned olefins. They caused stabilization issues. We think one of the important reasons of this is the high olefin content. Additionally, the products had 28% heavy fraction and low kerosene content. We don't want these results. Therefore, in next experiment, we change some parameters. We think that if we did preheating, we could reduce stabilization problems. So we added preheating at 200 degrees Celsius to the system. It was helpful. This time, the color of products is not as dark. It is an orange color. I think it looks cuter, but compared to orange, yellow is a lighter color. This still shows that stabilization issues continue. The good news is that the oxygen content decreased. The heavy product fraction dropped to 16%. The kerosene content increased to 39%. However, we still form jet fuel properties. We need to eliminate the heavy fraction and solve these stabilization problems. We came up with a solution for this. Let me tell you about it. Yes, fractionation. We separate STPO into light and heavy fraction up to 325 degrees Celsius. The stabilization problems due to the high olefin content not found in crude oil. This reaction bonds unstable and need to be protected from oxygen and light. So we removed the heavy fractions to keep STPO in the kerosene range. Did this work? Let me show you. Yes. Doesn't the product look so clean? You might be wondering if it turns black after waiting. We waited at it doesn't go bad. The analysis results are not bad either. Even at the fourth hour, the oxygen content dropped below 1%. There are no heavy fraction in the product anymore. And the kerosene content reached about 66%. And conclusion, NEMO alumino catalysts have given kerosene-like products successful result in the hydroprocessing of STPO. Preheating decreased the oxygen and water content in the products and increased the amount of kerosene. After fractionation of STPO, heavy cuts were removed. Kerosene and diesel conversion has increased. After the reaction, the oxygen content decreased to less than 1%. In the future, we aim to analyze the light fraction and focus on the reaction of heavy fractions to detail this study's future. That's it for my presentation today. Thank you. And I hope you found it interesting. Now
Thank you.
want to.
That was really, really
Want to
interesting. Thank you for your great
Thank you,
presentation. So over to Yannick now, and then hopefully we have a few minutes for questions at the end. Yannick, the floor is yours. Perfect.
Okay, perfect. Can you see my presentation? So I will go as faster as possible. So first, I will focus more in the co-processing in FCC units. So first, I would like to present a bit the ITQ. The ITQ is the Instituto de Tecnología Química. It's a joint public research center belonging to the Spanish National Research Council, but also to the Polytechnic University of Valencia, so Valencia in Spain, just here. We are more or less more than 300 professionals working in ITQ. But among this one, you have something like 30 researchers, a lot of PhD students doing actually the PhD thesis. So ITQ focus on different research activity, mainly in the topic of the energy, health, sustainability, and water. We are working a lot of the development of new catalysts, molecular design of new catalysts, and on the valorization of hydrocarbon and biomass is why we are participating in this European project. So to focus, as I said before, to focus on the possibility to use lignocellulosic biomass to produce liquid fuels, you have different alternatives. One of them is the use of thermochemicals processes, such as pyrolysis or hydrothermal liquefaction to produce an intermediate, which will be the biocrude, but this biocrude doesn't have the properties necessary to be sold directly as liquid fuels, commercial one. So they have to be upgrading. To do this upgrading, there is a possibility for refiners to use already existing processes such as hydrotreatment, hydrocracking, or catalytic cracking processes, or we already use it for crude oil processing, and to improve the quality of this bio-oil to produce a commercial liquid fuels. What is the problem? The main problem about pyrolysis oil or biocrude coming from hydrothermal liquefaction. The first one is the oxygen content. The oxygen content of this one, it's quite high for pyrolysis oil, as Khan said, could be something like 40 or 50% of the whole composition of the pyrolysis oil obtained from lignocellulosic biomass. Normally in crude oil, you find some less than 1% of oxygen. The other problem is the ratio between hydrogen and carbon. This one is quite low comparing to common crude oil, so you have to do something to increase this atomic ratio. All of this imply quite low energy quantity inside pyrolysis oil and biocrude from HTL, lower than the one normally obtained in crude oil. So this is why you have the need for a deep upgrading of this one to obtain something more similar to crude oil, and after to obtain commercial products such as gasoline, kerosene, and diesel for to be commercialized. Here to have an idea, I put some detailed composition of a typical product obtained by cracking of vacuum gas oil. And as you can see here in the small part, you have the gasoline pool, and between these 2 points, you have the diesel pool. So normally what you want to maximize as much as possible the quality of the gasoline pool, you want to decrease as much as possible the content of you want to maximize as possible the content of aromatics and decrease as much as possible the content of paraffins and yes, paraffins. For diesel, this is the exact contrary. You want to maximize as much as possible the content of paraffins and isoparaffins, and you want to limit as much as possible the contents of aromatics and B-aromatics, polyaromatics contents. If we take a look at the composition of a typical pyrolysis oil, you can see that it's completely different. Here you don't see any pure hydrocarbons. What you see, it's only carbohydrates. So here, after decomposition, thermal decomposition of the biomass, you obtain a mix of carbohydrates mainly composed by carboxylic acids, aldehydes, as Karen said, also phenolic derivatives, and also you can have the presence of some dimers or polymers still remaining here inside, such as the disaccharides or polyphenolic compounds. These products can bring some problems in processes such as hydrotreatment or catalytic cracking, because these products, heavy product, will enhance as coke and will provoke faster desactivation of the catalyst, giving a huge upset of the process operation. So in EBIO, the idea is to use first an electrochemical upgrading, which has a good idea to have at the same time you can do some oxidation and reduction operation of the pyrolysis oil. So in one side, you can try to depolymerize as much as possible the polymers still remaining inside the pyrolysis oil. In the other side, you can start to have an upgrading and a removing of the heteroatoms such as oxygen compounds, oxygenated compounds, and to obtain a much more friendly pyrolysis oil, which will be much easier to process in other processes. So here it's what you do after upgrading. We did some different upgrading grades in this project. And after upgrading of the pyrolysis oil, you can see that the obtained pyrolysis oil are much more similar to the one to standard hydrocarbon streams. So we already see the appearance of some paraffins, olefins, and also aromatics. And we see a huge removing of carboxylic acids and alcohols, aldehydes, and a partial removal of phenol derivatives. We do different grade of upgrading, and we use this kind of products to see the impact over the FCC co-processing. So as I said, after upgrading, here you have some data about the direct pyrolysis liquid, and here after the stabilization of the pyrolysis liquid, the first upgrading grade, and the stabilized and desoxygenated pyrolysis oil, the second level of upgrading. You can see that you are decreasing a lot the density of the pyrolysis liquid. You are removing a huge part of acidic compounds, so you are decreasing a lot the total acid number of the pyrolysis liquids. It's important because you can have a lot of corrosion issues in processes in refineries, so you have to take care of this parameter and to decrease it as much as possible before the processing. You are removing also a lot of water content, and you are removing a lot of heteroatom. You can decrease, in this case, in this example, the content of oxygen, and you are increasing a lot the hydrogen to carbon ratio, making it very much friendly for the co-processing. If you look, for example, the pyrolysis liquid at the beginning, it's not soluble in standard refinery stream, but through the upgrading, we are able to have good solubility, allowing the direct incorporation of this biogenic feedstock inside the FCC, for instance. Yes. So taking a look of the boiling point distribution of this different biocrude, you can see that we have already a quite high content of gasoline, of hydrocarbons or carbohydrate in the gasoline range, more or less 1/3, and also of diesel range, more or less 1/3. And still we have 1/3 of heavier boiling point carbohydrate in the range of the vacuum gas oil. So from here, we can imagine different strategy. The first strategy, the easier one, is to take the whole biocrude and to send it directly to FCC or to hydrocracking. Another possibility is the one that Seda showed before. You can do some fractionation to send only the light fraction to hydrotreatment, for example, bio, naphtha, kerosene, and gas oil to hydrotreatment, and to treat only the heavier fraction, 1/3 of the biocrude, to hydrocracking or FCC. Here I will show an example of the first possibilities with the direct incorporation of the world biocrude in FCC. So for this, at the laboratory scale, we used a unit called microdunner unit, which is a unit developed and patented by ITQ, which is a pilot plant which allow to mimic very well the FCC plant, industrial FCC plant, because this is entrained flow reactor. The catalyst is moving during the reaction. Is working in condition very similar to an FCC plant, same pressure, close to atmospheric pressure, same temperature, between 5 to 700 degrees. You can change it. And also with a very similar contact time between the feedstock and the catalyst in the order of 2 or 3 seconds, even if we can shorten it if necessary, because we can change the configuration of our reactor. So here what we did is to take a commercial vacuum gas oil and also a catalyst, commercial catalyst, which is an UC catalyst, a Y catalyst, provided equilibrium 1, provided by Tüpras, so coming from directly from real FCC, commercial FCC plants, and we set some different parameters such as the temperatures and the residence time, and we play with different catalyst to oil ratio, different reaction at different catalyst to oil ratio, to change to have an evolution of the conversion of the biocrude. And for this, we did some different blending, starting from the pure vacuum gas oil, and we introduced an increasing quantity of biocrude inside. The first point is to see the impact of this incorporation of the activity of the catalyst during FCC processing. So we saw that at very low blending level, incorporation level of 5, 10, or 25%, we have very few impact over the overall conversion of the FCC. We start to see higher impact at higher conversion level, but it's still quite controlled, meaning that the upgrading of the electrochemical upgrading makes a great job in this case. You can see some difference, and it's better to work with the higher upgrading biocrude than with the lower upgrading biocrude. Concerning selectivity of products, we saw that the incorporation of biocrude inside FCC involve a decrease of gases production. So it's a good news, because it makes sense to put directly the whole biocrude inside FCC. It's not necessary to only put the higher boiling point carbohydrate inside, because we are not losing too much products as dry gas. And we can see that at low incorporation level, we have very limited impact over the different product selectivity, such as gasoline, kerosene, and diesel LCO here. And we start to have more important impact at higher blending level. This is why we are producing, at higher blending level, we are producing more coke due to the biocrude, and this coke have an effect of the recracking activity of the catalyst, meaning that we are obtaining less heavy, more heavy fraction at the end of the FCC co-processing on less light fractions. To give you an idea of what's happened to oxygen during FCC co-processing, here you have some yields about the water produced, CO and CO2, and we saw that the main part of the desoxygenation takes place through dehydration. If you take a look of the products obtained after cracking, here you have the starting SPO biocrude and the obtained products after co-processing. I think here it's at 55% of SPO inside the co-processing. We can see that we have a very quite easy removing of oxygenating compounds such as alcohols and carboxylic acid, but you have some refractory phenomenon to remove very efficiently phenolic compounds. Here, just to take a look of the influence of the co-processing over the quality of the product obtained, we can see. So here you have for the SPO or for the SDPO in the right side. And here you have the word composition of gasoline, kerosenes, and diesel LCO fraction. And we can say that the incorporation of the biocrude in this case improve slightly the quality of the obtained gasoline, because we are obtaining a gasoline which have a higher content of aromatics, and it improve also the quality of the kerosene and of the diesel, because we are decrease of the biaromatics and monoaromatics compound inside this different fraction. The point is that we have an accumulation of oxygenated compounds, mainly phenolic derivatives, and which can represent, well, let's see, with SDPO, which can represent up to 5% in the case of the gasoline and to 20% in the case of the kerosene. So even if in Europe you don't have any special legislation about the content of oxygen in this kind of products, we think that it will be better to try to remove as much as possible these phenolic compounds, because this one can bring some issues about corrosion deposit in fuel system, can reduce the lubricity, and can have also an impact over the emission of thermic motors. So from my side, it's okay.
Thanks, Yannick. Thanks for the lovely presentation there. So I wrote to all the viewers, we're slightly overrunning, but we just have time for some few questions. It would be a shame to close without any questions. Roman, have you seen any, which of these questions do you think would be a good, perhaps
yeah. Fortunately, one of the questions was already answered by another attendee. So thanks to Przemysław. But let's start with the first one by Hak Gamoret. What are the most important requirements for pyrolysis oils to be refinery friendly? Yannick, you wanted to answer that.
Yeah, typically what we want is to limit as much as possible the content of heteroatoms, oxygen compounds, because it will give some trouble to have a good blending with fossil fuel derivative streams. And what we want, gasoline and diesel, for example, are high hydrogen to carbon ratio products. So you have to try to incorporate to keep as much as possible this parameter of hydrogen to carbon ratio. If not, you will not be able to obtain the product you decide after co-processing.
Thank you. Then maybe to Seda and Chan, NEMO and COMO catalysts were discussed. I think all of them are alumina supported. Why was this catalyst chosen?
I can say about this one. in EBIO project, we are planning to maximize the jet fuel yield. If you use much more acidic support material, this may cause some cracking and increase the naphtha production. That is why we are using this moderate acidity support material in our trials.
How long did you run the hydrogenation tests?
We have run these reactions 5 to 6 hours for now. But for the last trials after fractionation, we have obtained much more promising results, and we are planning to continue to test this catalyst for longer hours.
Thank you.
Maybe also alumina is resistant to high temperatures and high thermal stability. This allows the catalyst to operate without dehydration and hydroprocess reactions that require high temperatures.
Thank you. Then how did you remove the water from the oil before upgrading?
We are just draining it and using some fractionation to decrease the level of water inside, especially for the heavier cuts. But it may still remains in some lighter cuts as well.
Yes, at some point you get phase separation, and then you can easily remove it. Let's see.
Let's just have one more question and then
One more question. Then we maybe do the last one because it's quite related to the electrochemical upgrading. How do you rate the pre-treatment technology electrochemical upgrading if you use a TRL level between 1 and 9? So maybe I can answer this one. So the project aims to achieve TRL4, and that's what we will achieve. So it's still a lot of work to go to larger pilot or even industrial operation. So we are now running 3 units that work at TRL 3-4. Yes, all the other questions that we couldn't answer now, we will answer on the website, and the recording will also be at the website very soon. The one for this webinar, but also for the previous webinars. So please have a look, and thanks for everyone, especially to the speakers, Sedat-Can and Yannick, and thanks to the attendees for using the time. Thank you.
Thanks,
have a good day.
Roman. Okay, thank you everyone. Bye-bye.
Thank you very much.
Thank you.
Thank you.